All right, welcome to our lecture today about the life cycle of all stars. Previously we've talked about the sun and that it's a medium-sized star and that it also is one that is producing fusion. It is currently producing hydrogen into helium, which puts it into that hydrostatic equilibrium shape, meaning that there is pressure being pushed outwards due to that fusion, and there is pressure being pushed inwards due to gravity. So it keeps the sun in a nice sphere shape. All stars are not always doing that though. Some are in their beginning stages, some are closer to the end stage. And so we're going to talk about what that looks like because there's all different types. I like to say that stars are like McDonald's French fries. You can get a small, medium, large, extra large, supersize, whatever. So stars can kind of be that same way. So in our Canvas course, you're going to want to pop on down to the space unit. And we are jumping down to the notes that say life cycle of a star. So go ahead and click that. I already pulled mine up though, so I'm just going to pull it up here for us and make it bigger. So life cycles of a star. So as you can see, this is a picture here. And we're going to go through and talk about the different stages in which a star can go through. Some are more violent than other stages, as you can see. And so we'll spend quite a bit of time talking about these different stages and the importance of how motion and gravity and speed all play effect on what's happening with that radiation and what's happening with that heat. So the first stage, ironically, is a stage that we've already talked about when we were talking about our solar system, which is a nebula. So once again, the idea is that a nebula is kind of just the nursery or building blocks for anything to take shape in space. So it is a cloud of gas and dust, and we'll talk about today, it becomes full circle. It's kind of like Hakuna Matata, the circle of life in space, is that a nebula was created from something else, which is a supernova, and we'll get there and then kind of wrap it all back around. So a nebula is a cloud of gas and dust that was created by a supernova. Star ending its life bursts into a big explosion and creates this gas and dust. And then it starts to slowly, the nebula starts to slowly come back together. And that's where this is saying here. It begins with a slow accumulation of gas and dust. And so as the molecules start to get closer and closer again, or the particles of matter start to get closer and closer together again, they start to increase their temperature and pressure. So temperature and pressure is slowly increased as it gets back closer and closer together. And if you Google nebulas, there's a ton of them. My personal favorite is the Sombrero Nebula. It really does look like a sombrero. But you can look at a whole bunch of different things. So this one here, I believe it's called the Crab Nebula. It is to look like a crab. I don't see it, but it's there. So what happens after the nebula stage is that it's a cloud, gas and dust. Lots and lots of hydrogen is there. Hydrogen is the most abundant element in all of the universe. So in this nebula, there's tons of hydrogen, which is also the simplest Miss element. It's kind of the building block of everything else. So what happens in the nebula stage is that cloud keeps getting closer and closer and closer together as gravity is pulling those particles together. So it jumps into what we call the protostar stage, meaning that it's getting kind of arranged to want to do fusion. It's just not there yet. So it starts to kind of condense into a more smaller nebula that's still kind of a cloud, but it starts to spin. So think of that accretion process we talked about. This is happening here too. So it starts to spin because gravity is pushing on it, because all those particles have a mass and they're starting to create that energy of gravitational forces, and they start to pull together a little bit closer. So we go from a nebula, which is just a cloud of gas and dust, to a protostar, which is a object that is becoming more organized. The temperature is increasing, the pressure is increasing. The next stage is probably the most important one, and we call this the main sequence star, meaning that it is doing nuclear fusion. It is taking hydrogen atoms, pushing them together to fuse together to form helium. That's what this is talking here, is energy released from nuclear fusion counteracts inward force of gravity. So we have this nuclear fusion that's happening here in this thermal pressure, and then gravity's pushing in there. And we once again call that fusion, and that's hydrogen into helium. And when we have fusion happening and gravity happening, we have a star that is on the main sequence. Now, depending on its mass is going to depend on how long it's going to stay on the main sequence. Sometimes if it's a really massive star, it's not going to stay there nearly as long as a much smaller star. So the sun, for example, has been on the main sequence for about 5 billion years, where it's about midlife type of star. So we have about 5 billion more years before we have to start worrying about what the sun is going to do. So it's about mid-age. So we have nebula, protostar, and then our main sequence, hydrogen into helium. I'm going to skip over the questions here. So what happens is that it's fusing together hydrogen into helium, and over time, that hydrogen is going to all fuse together, and then you're going to be out of hydrogen, but you're left with a whole bunch of helium. And so what this is saying here is once a star has burned up all of its hydrogen, its core starts to become really unbalanced, and so it loses that hydrostatic equilibrium. It loses this picture right here, that pressure of thermal and gravity, and so it starts to get almost like wobbly, if you want to think about it. And so it gets wobbly, and some of those layers are going to start to swell up, and this is what we call the red giant stage. Once again, remember we talked about things that appear red and orange and yellow in space are actually much cooler. So the outer layers of the star start to swell, making it cooler and red in its appearance. The star Betelgeuse, which is close to us in our solar system, it's actually in Orion's constellation. I think it's one of his shoulders. It is a red giant, and you can actually see it out in the night sky, and it does have a slight, it's not perfect, but if you look at it long enough, you can tell that it's definitely a much more orangish type color. Maybe I wouldn't say like deep red, but you can tell that it is a different color. So what happens is that as it starts to swell up, the core starts to oh, we've got heavy elements, and so it starts to condense because gravity once again is pushing it together, and it starts to fuse together helium. So instead of hydrogen, it's now putting together helium, and that will then form lithium and other different types. I'll show you here in a minute. So core will condense and then heat up to stay balanced, and so it starts to stay balanced by burning helium or fusing together helium. In large stars, this is going to happen many, many, many times. So it will stay and keep fusing different elements. It will press down, fuse that element, swell up again, and then press down, and then fuse together another element. It keeps going through this process. Whereas a smaller star like our sun will probably only do to helium, maybe to carbon or lithium, and then it's done. So the beginning of the end. The red giant is kind of it's like farewell to the universe. It's that it's going to start going through a collapse period. So after hydrogen exhausts itself in the core, it will once again start to lose its hydrostatic equilibrium, and the core collapses, and that's going to allow once again that red giant stage. Here's a picture. Here's Betelgeuse. So once again, this is Orion. You can always find that one easy in the sky by looking for these three stars that are really close together. Orion is a hunter, and I once again, I don't see it. I can kind of see the body, but Betelgeuse is here on his shoulder. So go out and take a look. It's actually visible all year long. So once again, if you have downloaded that sky tracker, it should help you find it. So we've gone through nebula, beginning of a star, formation of organization, and then we have our main sequence, hydrogen into helium, fusion, and then our red giant stage is it's wafting just a little bit. Now, depending on what size star it is, this is where we can have almost a break in our designation with a red giant. If it's a small, medium star, it's going to go one way, and if it's a large or massive star, it's going to go another way, and they kind of end two different ways. So let's start with the sun, which is our small to medium sized star. So after the red giant stage, it is going to compress down, and it doesn't have enough mass to fuse anything else together. So what happens is that it's going to have the core of the star that has been super hot due to that fusion process, but there's nothing to hold those outer layers together. So they start to diminish into a surrounding area, creating a planetary nebula, which can make way for solar systems and other things to form. And what you're left with is what we call a white dwarf, which is just almost like a cinder of the core that is just radiating energy. It's no longer producing energy because there's no more nuclear fusion. It's just radiating out. And these white dwarfs are super massive because all of those elements have been pushed really, really, really close together. And so we're left with a white dwarf. White dwarfs will eventually turn into black dwarfs because they will run out of radiating energy. They'll run out of heat, and then they just kind of are then a rock just floating in space. So that's for a small and medium. So the track for a small medium star is nebula, protostar, main sequence, red giant, white dwarf. The more exciting ones. So let's talk a little bit about our massive stars. So once again, this would be the core of a star. So right now, sun is doing hydrogen into helium. It may burn a little bit of carbon in that red giant stage, and then that's when it will slowly dissipate into a white dwarf and a planetary nebula. Larger stars, that Betelgeuse, for example, that one that I showed you, is a massive star. So it's right now probably going through one of these phases where it is now fusing maybe carbon to hydrogen, hydrogen maybe to neon, neon to magnesium, silicon. And then once again, look, we have that iron, this iron that we keep talking about. And iron is a very stable element. Think about it once again with the X-rays, it won't let anything penetrate. And so same thing in a massive star is once we get to that iron, when we fuse together silicon to get iron, it can't fuse anything anymore. And so it becomes super unstable and it goes kaboom. And then we get our supernova. So that's what this says here. Iron is the most stable element and can't be fused together anymore. So you get, boom, your supernova, which is a huge, massive explosion. We have pictures of them that have taken place from ancient Chinese people who have written that all of a sudden there was this huge flash of light. Now, I think that took probably thousands of years to get here, depending on where it was. But we can visibly see a supernova. So once again, that's going to be a massive sized star. It's reached the point where it can't fuse anything else together. And so all that energy just says, I can't do it anymore, and then goes outward into a huge explosion. So in a large star, we've got nebula, protostar, main sequence, red giant, supernova. Now, depending on what kind of star it is, this supernova can create, once again, a nebula, which then circles it all the way back to our nebula. And depending on the material there, it might be able to make another star. It might be able to make a planetary nebula too. So it can have one or two functions. Or if it's really, really massive, it then can go into our last possibility for a massive star, which is our black hole. Oh, sorry, I forgot this last part. So let me go back. So with our massive star, huge explosion, it can form a neutron star, which is kind of like our white dwarf, just the core that is left over. And that's kind of in our massive star. If it is a supermassive star, instead of that energy exploding outwards, it implodes inwards and creates what we call a black hole, which is the most massive type of object we can find in our night sky. Scientists are able to confirm them. Einstein was the first to say that, I don't understand it, but math shows that there should be something that looks like this, but we can't see it. hence it was black. That's why they named it that. And then Stephen Hawking is the one who did all the math behind it and said, I can mathematically prove that there's one here, here, here. And so these are really massive objects, and they have so much mass that they can hold things together, and so that it can even not let light escape. So that's where this is saying very massive star is going to implode and create this black hole. So we've gone from nebula, protostar, main sequence, red giant, supernova, black hole. So just to kind of give you an idea, these heavy elements that are being created due to supernovas. So supernovas release a whole bunch of elements that can be made into different things. And that's where we get this creation of different types of elements that we can see on our periodic table. So in our neck of the woods, if you think about it, the